Hey, what's up everyone? Good morning, good afternoon, good evening, whatever time of day you're deciding to watch this video. So this is going to be a video walkthrough of the Energy Budget Lab. So this is another kind of really interesting lab where we're going to essentially investigate, what's coming in from the sun versus what's leaving from the surface of Earth. And we're essentially going to do that in three ways. So first, we're going to look at sort of like the general idea of incoming versus outgoing and what happens to, what's trying to come in versus what's trying to go out and what's kind of impeding within these interactions. And then we're going to get a little bit more detailed, so look very specifically at what's happening, again, between incoming and outgoing. And then we're going to look at 3 locations in the Northern Hemisphere and their specific energy budget. As always, if you have any questions that come up while you're doing this lab, please don't hesitate to reach out. I'm here to help. Office hours are always open. Shoot me an email, shoot me a text, especially if this is for the online class. If you're emailing me, please include any sort of like screenshots if you're having any errors or anything like that. It's easier for me to diagnose what's happening and to help you if I see what's going on, rather than just like, it's not working. I would love for you to be specific and show me what's not working, or what you may not completely understand. So let's get into it. So this should be initially what you see when you open up the lab. As usual, make a copy for yourself. So yeah, hopefully you've talked about energy budget in your class. So hopefully this won't be kind of like out of the ordinary or out of left field, but some helpful definitions here. When I do SW, it's shortwave, LW is long wave, and some basic radiation laws. Basically, the temperature of an object will then dictate the amount of radiation emitted by that object. So hotter objects emit more radiation, cooler objects emit cooler objects emit less radiation, and then the wavelength at which most of that radiation is emitted. So there's like a key components within that. And so when you put those two laws together, the idea here is, if we increase the amount of gases that are able to absorb and re-emit outgoing radiation, what's going to happen to the temperature of the planet? So my analogy to help with this one is whatever shirt you're wearing right now, if you put 15 of those on, what's going to happen to your body temperature? So basically, if you increase the amount of a gas that's in our atmosphere that traps outgoing radiation, what's going to potentially happen to the temperature of our planet? And that's how you can kind of think of a lot of our what we call greenhouse gases in our atmosphere. They're basically like the planet's blanket. So it's not trapping what's coming in, it's trapping what's trying to leave. And just like if you were to put your hand over your arm, and you can feel your outgoing body heat, like without touching your arm, right? You can feel your outgoing body heat. So our planet is also emitting body heat, essentially. And our gases, our greenhouse gases in our atmosphere help trap what's going in. So I want you to also give me why do you think solar radiation is shortwave and long wave? If it's been a minute since you've talked about short and long wave, maybe refer to some of your course resources. And then this definition of albedo. So then next I have a table that is going to correspond to this graphic here. And this is a graphic that is really important when we're thinking about the energy budget. And what I've done in this table is I've tried to color code kind of which part of the graph you should kind of be looking at. So red is indicating what's coming down by the sun, which is the left side of this graph. And the bluish color is meant to be kind of your focus over here on the right side of the graph. So hopefully that color coding helps out a little bit. There's one in black because it kind of extends throughout the whole wavelengths here. So to give you some context of what we're looking at, on our x-axis is wavelength, and then on our top y-axis in this top graph is spectral intensity. So essentially, in a sense, heat or heat in a sense. And so what you see are these sort of bell curve looking things, but underneath that bell curve is sort of like shaded in almost kind of curve with some loop-de-loops in there as well, or some valleys, I guess, if you will. And what's essentially happening here is this is sort of the temperature of the sun as it's kind of reaching our atmosphere, and where there's a gap between the curve and the shaded part is interference. So the shaded part is what's actually making it through the atmosphere, and the space between the shaded part and the curve is what's not happening, or what's not being transmitted. So essentially what I want you to do within this table is sort of dissect everything that's happening in this graphic. So initially I ask, what are the 3 types of wavelengths that are coming in by the sun? Those are indicated here. What's the 1 type of wavelength that's emitted by Earth? That's indicated here. And then there's percentages that are indicated at the top of this as well. You don't need to go to any outside resources. Everything you need to fill in on the table up above, you can find in this graphic. You shouldn't have to go anywhere else. And then I ask 2 processes that interfere with what isn't being transmitted. I don't want to say them out loud, but again, it's indicated here. And then the idea with the second part, the gases responsible for that interference, either for the sun side or the earth side, essentially what you want to do is basically, or the idea here again, and you can take like a piece of paper and put it up to your screen if you want. I can try to just kind of like get rid of this stuff here, pretend we're not looking at this. So essentially what you want to do is notice where there is total interference, in a sense, on whichever side we're looking at, and sort of try to find which of these 6 gases are responsible for the most amount of that interference at that particular wavelength, right? And by the way, apologies that I did not fully explain this part. So this panel here is the interference of what's not happening with what's being transmitted through the atmosphere. And these 6 panels are basically putting, you're adding all of these 6 together to give you this panel here. So a silly way you can think about it, this is like a fully composed dish, say like a pancake, and these are the 6 ingredients of a pancake. So like flour, milk, oil, sugar, some maple syrup and butter or something, and then you put all these things together and voila, then you have a delicious pancake. So same thing you will do for this right side here, but instead of, looking at what's interfering here, you'll look at which gases are interfering sort of on this side of the graph. So that's the intent with this first graphic. Again, this is very general, just what's coming in and leaving, and the gases or scattering regimes that are responsible for what's not actually making it all the way through the atmosphere. Then our next activity is looking through the surface energy budget. So we're going to look in further detail of what exactly is occurring with what's incoming and outgoing, with another table you're going to fill in from this graphic here underneath. So this table, every row has words in it, and those words correspond with an arrow over here or underneath on the in this graphic. The only 2 arrows that do not have a place in the table are these 2 nuggets here. Oh, I want to draw. Are these 2 nuggets here. So don't worry about these. Doesn't mean they're not important, but there's just not a space for them in this table. But everything else you should be able to match almost exactly to what you see here in this graphic. So if you're having any issues with that, of course, as always, reach out. Oh, so sorry, I forgot to mention one other thing. Within or underneath the words per arrow, you'll see 2 numbers. One is the value of energy, which is in watts per meter squared. And then another one is in parentheses, and that's the percentage. So you don't have to do any other math here at all. You're literally just matching the words with the arrow and then inputting those values into the table. These values are going to be important because you're going to do two quick calculations. We're going to look at, you're going to calculate the albedo of Earth, which is basically you're going to do shortwave reflected divided by shortwave incoming, and you're going to do the energy with that, not the percentage. And then the second calculation you're going to do is just simply subtract shortwave minus longwave of the net, net absorbed minus net emitted. And that is all spelled out down here as well. I've given you the equations for both. Show your work here, include units when possible. Albedo is a unitless ratio, so it's going to be watts per meter squared divided by watts per meter squared. Those units cancel out, then you times 100 for a percentage. Excuse me. And then just some sort of like review questions here on the greenhouse effect. What part of this table and figure do you think is the greenhouse effect? There's one very specific component that is the greenhouse effect. And then I want you to also tell me about feedback loops in earth sciences. So perhaps you've gotten to this in your classes, I'm not entirely sure, but it is a really important concept when we're talking about things like climate change and climate variation. So it's still a good, useful thing to look into. So you can use outside resources for this, or if you have covered it in your classes, then talk about them here and tell me what you got. Please make sure that the examples are related to earth science and not like, I don't know, if you just try to Google a positive feedback loop or a negative feedback loop, you may get things that revolve around like human health. Like some students have tried to tell me about childbirth. I'm like, we're not doing childbirth in this class. So please make sure they're related to climate. And I want you to include several steps for each loop. I want you to be specific here. I don't want you to be general. So please make sure you're using very specific actual loops. And if you're having any trouble with this or need any assistance, do please feel free to reach out and I can provide you resources. Then your final activity here is going to once again utilize a spreadsheet to help us graph and calculate some data. So your first task is going to be, first of all, to copy this spreadsheet to your own drive. So again, you're going to go up to File and make a copy and copy it to your own drive. If you're choosing to just copy what's on the sheet itself, please, please, please take note there are 2 sheets included in this entire file. So make sure you're either copying both, but I think the easiest way again is just to simply make a copy, just like you do with the labs, or download this. If you're using Excel, for example, you can download this as an XLSX file and then open it from there. Then from here, I ask you to actually map the locations first. So if you've never used MyMap before, it's really cool. I think I've shown you how to do this potentially in another lab, or if I'm thinking of another class, I apologize. But anyway, so if you click on that link, you can go to Get Started, and essentially you are going to then search locations. You don't have to include the latitude and longitude, but simply when you search a location, like say I did Reykjavik here, or if I did Regensburg, Germany, like when you search the location, all you have to do is hit the Add to Map button and it adds it to your specific map. So once you have all 3 locations that are indicated in the spreadsheet, then you just are going to zoom out from where those 3 locations are so you can see all of them in one place, and then just take a screenshot of that and include it in your lab. This is just so we can get a reference for where these 3 locations are at: Dead Horse, Alaska, Beijing, China, and Kampala, Uganda. So just giving us an idea of where these locations are without having to do like what we did in Lab 2, where I gave you a latitude, longitude, and you plot them on a map, right? This is just kind of an easier way to do that exercise where you don't have to include both latitude and longitude. And then for there's 2 parts, there's 2 sheets within that spreadsheet. So you're going to create a simple graph of just the monthly average insolation data. You are not going to include the annual average, but the annual average you're going to use to help answer a couple of questions beneath. So essentially how to do that, you're just going to select these cells and let's go to insert and chart. And there's kind of two ways that this will sort of come up. You can either, however you want to do this is essentially fine, but this is one way that it will come up. You can also do switch rows and columns, and it has the months on the x-axis, and each location is then indicated by the color bar. I'm not really picky. I want you to choose the one that tells the story the best for you and gives you the best understanding of this content. Just make sure, as usual, that all of your axes are properly labeled. So this would technically actually be the proper x-axis for this one. But say if we, again, did it sort of this way, then the x-axis is not location, right? So just make sure you're changing that if you are deciding to do this particular graph. And I have our things to remember here. So first of all, give your spreadsheet a name, provide comprehensive titles, put your name in the subtitle and access titles, including units when applicable, so that I know what everything means. If you want full credit for that graph, this is now, gosh, our third or fourth graph actually. So if you're missing any of these components, then you won't get credit for the lab, for that graph. So if you want full credit, would suggest for you to do that. Then the next component here is looking at the budget. So in the second tab, there's a monthly budget page, and I basically have each of the locations sort of separated out here with their incoming, outgoing shortwave and outgoing longwave radiation. So this is taking not just what's coming in, excuse me, but also what's what's leaving. Oh, excuse me. And so to calculate the net radiation, it's rather simple. I'm going to do it outside of where I want you to calculate it. You should be calculating it in column F. But I'm just going to do it off to the side here, again, just so we're not copying and pasting exactly what I do. But the idea here is really simple. You're just going to tell the spreadsheet to do a really simple calculation. First thing we're going to do, just like we did with our other functions, the equal sign is going to be our first indication to the spreadsheet that we're doing some sort of mathematic function or regular function within sheets. And then essentially, as it said in the directions, you just do incoming radiation, so let's click on that cell, minus sign, outgoing shortwave, minus sign, outgoing longwave, and that is your function, and just hit return, and that will give you a value. You don't have to type that in for every single cell. An easy way to do that, if it doesn't already automatically say, do you want to autofill, then just go to the cell where you did that initial calculation. There's a little blue dot here on the bottom right corner of this cell. You're just going to go to the hover over it, and your cursor becomes a plus sign. And with that plus sign, just click and drag all the way down, and it does that calculation for each cell that is selected. So that's your first task. Then your next task is to calculate the total net radiation for that year. And to do that, where it initially says 0, because we auto-filled that or used the blue dot bestie to do that for us. But to do the total, you just use the sum function, which is really a really neat function. Again, first thing you do, equal sign, boop. And then it is already anticipating what it wants me to do, but I'll just type it in anyway. Sum, open parentheses, and then select those values and close parentheses, or those cells, excuse me, and then just hit return, and it gives you a full sum or total of the entire net radiation. So you're going to complete that for each of the locations, and then what you're going to do is copy and paste your completed table here. Again, this is so I can make sure that you're doing the calculations correctly. And then you're going to answer some questions on all of that data. So that is the walkthrough for the Energy Budget Lab. Might be a little complicated initially, like with those figures and kind of trying to dissect them, but I believe in you. You can do this. And as always, reach out if you have any questions or need any sort of clarification. I'm here to help and assist in any way that I am able to. Office hours are always open, emails always open. You can always shoot me a text. I hope to hear from you if you're confused, and if not, I'm just going to assume all is groovy. Thank you so much for watching this video, and have a lovely rest of your day. Thanks.